Section 10.3 Activities and Activity Coefficients for Electrolyte Solutions. The chemical potential of an electrolyte is the sum of the chemical potential of the cations and anions. And if we have coefficients in front of the cations and anions, mu plus and mu minus should be put in front of the chemical potential of the corresponding ions. For example, the chemical potential of aluminum sulfate is 2 times the chemical potential of aluminum 3 plus and 3 times the chemical potential of sulfate because of the subscripts. And over here, I'm not talking about aluminum sulfate solid. I'm talking about this aluminum sulfate fully dissolved in water. The arithmetic mean ionic chemical potential is this. So we need to take the coefficients into account. So this mu plus minus the arithmetic mean of ionic chemical potential is mu plus times nu plus times mu plus. So right here. Okay, that's the total chemical potential of the electrolyte, divided by the number of ions. So in this case, it's going to be 5 for aluminum sulfate. In general, it's nu plus nu minus. Again, you look at the subscripts. So in this case, for aluminum sulfate, the arithmetic mean, or simply the average ionic chemical potential, is 2 times the chemical potential of aluminum 3 plus and plus 3 times the chemical potential of sulfate, and then divided by 5. Because if you dissolve just 1 aluminum sulfate in water, you get 2 aluminum ions and 3 sulfate ions. So we're taking the average of the chemical potential of this 5 ions. Alright, so we have this equation here. If this nu is the sum of nu plus and nu minus, then we have the average or arithmetic mean ionic chemical potential to be the total chemical potential of all ions divided by the number of ions. That makes sense. And this is a more general equation. If we specify a standard state, we just put a superscript naught on top of every single mu. Again, this superscript naught stands for the standard state. And then we can calculate the difference between this mu plus minus and the standard mu plus minus. So this is just simple mathematics, and we do some reorganization here. And now you can see we have mu plus minus mu plus naught. That's actually the logarithm of a plus times RT. Over here, mu minus is equal to mu minus naught plus RT times the logarithm of the activity of the negative ions. And in this case, we have RT as the common factor here. And then we have mu plus times the logarithm of A plus, and mu minus times the logarithm of A minus over here. This is the different part. And then we can actually put this together. Why? So we can see this part is A plus to the power of nu plus. This part is A minus to the power of nu minus. And somehow we can also introduce this 1 over nu into the logarithm. So it's this form. If you look at this, and you know what geometric mean is, this is the geometric mean of the ionic chemical potential. So let me give you an example. What is a geometric mean? So if you have two numbers, 2 and 4, the arithmetic mean is just the average. That's 3. What's the geometric mean? Geometric mean is this. It's 2 times 4. You get 8. And then you take the square root of it. So that's square root of 8. It's 2.828. That's the geometric mean of 2 and 4. So what about the geometric mean of 1, 2, and 4? Well, you just do multiplication again. 1 times 2 times 4. you get a to the power of 1/3, that's 2. So the geometric mean of these three numbers, 1, 2, 4, is 2. What about the average? Well, or arithmetic mean. The arithmetic mean or average is 1 plus 2 plus 4 divided by 3. That's a different number. That's actually 2.3333. So again, the geometric mean is different from arithmetic mean. Alright, get back to this. A plus minus is thus the geometric mean of the activity of the cations and anions. And the chemical potential, actually, the of the electrolyte is proportional to the arithmetic mean of the ions. So why there's a difference here, just pay attention to this logarithm. The logarithm can turn the geometric mean into arithmetic mean. Alright, so now we'll look at this activity to have a similar relation between the activity and the concentration for non-electrolyte. We define this M plus minus to be, again, the geometric mean of the molality of the cations and the molality of the anions over here. And then we have this activity coefficient. The activity coefficient is simply the activity divided by the concentration. This concentration is in the unit of 1 mole. I'm sorry, just the number of moles of the solute per kilogram solvent. Now let's look at this aluminum sulfate again. This M plus minus is the geometric mean of the molality of this aluminum 3 plus and the molality of sulfate. Similarly, we have this equation for activity. Just remember, activity is the concentration times the activity coefficient. So we have activity coefficient here. Look at this geometric mean of the activity coefficient. Again, it's the geometric mean of the activity coefficient of aluminum 3 plus and sulfate. Okay, now you may wonder, why do we need this anyway? Can we just use gamma of aluminum, gamma of sulfate separately? Well, the problem is this: it's impossible to separate cations from anions in a solution. So you are always measuring the collective properties for cations and anions together. So that's why it's convenient to just define this gamma plus minus. And it's probably the only way to describe the activity of cations and anions. You just cannot separate these two.